So we've gone through the syllabus, course information / assessment. Let's go over an introduction to modern aircraft aerodynamics. So here is an Airbus 380. It's interesting that we were taking aerodynamics at a time where when you look at airports, you'll see that most aircraft have been grounded, and air traffic has stopped for the most part of it, and it's so tough to it's hard to travel. I mean, you have to think 10 times before you decide you want to take a trip, because I personally wouldn't want to have them stick something up my nose. It's just seems to be too painful and too inconvenient. That at least the sound of it sounds just too much of a stress that I would not want to go through. But it's interesting times, but we will go back to flying again. Maybe we will be back, maybe not in the coming years to fly in electric airplanes, but we will be back flying, and in probably the near future or the medium future, we will be flying in electric cars, just like we will be driving in electric cars. We'll be flying in electric airplanes and driving electric cars. So these are things to keep your eye on as you are planning your career. At least that's my hunch. So here's an aircraft. So let's go back to the future, or back to today, not the future, back to yesterday actually, when we were flying. You look at an airplane, and let's just look at how it flies. An airplane has a weight, and okay, so an airplane takes a payload from point A to point B. So the payload without the fuel is placed in the fuselage. That's where you have your passengers, and that's where you have your cargo. So that's the payload, pretty much. There's a lot of fuel. You can have a lot of fuel weight in the wings, which can weigh as much as half the airplane weight for long-haul travel. So you don't want to discount that. But how does so there's the weight of the airplane, and that weight of the airplane is being counteracted by the lift generated. And how is this lift generated? The lift is generated by the wings. So the wings have some type of lift coefficient, and the amount of lift that is being generated by the airplane depend on the shape of the wing, and depend on how fast the airplane is moving, actually how fast the velocity squared, as well as the area of the wing. So what the engines do is they create a thrust force that pushes you forward on the runway to achieve a critical speed. And once you achieve a critical speed on the runway, your lift will be at least equal to your weight. And in fact, to take off, you needed to exceed the weight so that you can accelerate in the vertical direction. So you accelerate in the vertical direction until you get to your cruising altitude, and then you manage your lift to be exactly equal to your weight, such that you don't have a net vertical force. And the only force that the engine is doing is to push you forward and counteract drag. But if you look at this is the fuselage, that's the payload, and these are the wings that are doing the weight. But let's look at it. We have not just one wing. We have these lifting wings, and they also have some little wings that are connected to them at the trailing edge. There's a little triangular wing at the tip. There is the elevator right here, which is also another wing. You have the the rudder, which also has a little control surface over it. So if I move to the next slide, you'll see that we have different kinds of wings. We have the wing that generates the lift. We have the tip vortex winglet. We have the rudder, the elevator over here that stabilizes you stabilizes your pitch, angle of attack, and you have different type of control surfaces. So we have the wings, right, which is the main wing, the stabilizer, and the horizontal and vertical stabilizers, as well as you have control surfaces that the pilot can control to change direction, to change altitude, go up, go down, take off, land. So these are the surfaces, the black ones that they control. But if you look at any one of those surfaces, what is its main objective? Its main objective is to create a force, and the force would be perpendicular. Typically, on average, it's perpendicular to the area of the wing, but more accurately, the force is perpendicular to the direction of motion. As we might have seen in fluid mechanics, it's perpendicular to the direction of motion, which we call a lift force. And then there's a force that is parallel to the direction of motion, which we call the drag force. But we will come back to that. I think the main the takeaway message from those two slides is that we have lots of wings and control surfaces. And if we look at, and they relate, their shape relates to this lift coefficient over here, which relates to how much weight that airplane can carry. So the whole design process of an airplane is, in terms of weight, load, velocity, so on, is based in this lift equation. And the one common theme between all these lifting surfaces is the cross section. So here's our wing. So let's just do some nomenclature. If I take a knife on this lift generating wing and cut it along this line, I will expose this cross section. So now you look at it. You cut it with a saw. You cut it with a saw. You cut the wing. So let's define this as my leading edge. So if you look at the wing as a knife, it has a leading edge and it has a trailing edge. So the leading edge is the edge that cuts the air. The trailing edge is where the air leaves, the cut air leaves the wing. And now if I take a saw and draw a line from the leading edge to the trailing edge and take a cut, I'm going to expose this aerofoil section. And unlike a knife, which has the thinner part at the leading edge, the airfoil has the thicker part at the leading edge and the thin part at the trailing edge. So that's why they are different applications. The knife is there to generate pressure, to generate a lot of pressure to cut through. And you'll notice that a knife actually also resembles high-speed aerodynamics. But in low-speed aerodynamics, non-supersonic, so below sonic speed and below, this would be the shape, which we call low-speed aerodynamics. The shape is the normal airfoil section. As you can see, I flipped it left-right, so the writing is flipped left-right, just so you can orient you in the same direction as the plot over here. So at this section, the air flows around it, and that air comes in at a high speed. Typically, an airplane moves anywhere between 300 to 900 kilometers per hour. So you're talking 100 meters to maybe 100 to 300 meters per second. that's close to the speed of sound. And as the air comes and hits this wing, it will split left and right, just like when you're cutting your bread or your steak or whatever your favorite food is. It splits left and right, but it splits in an uneven, unequal fashion. And that generates a difference in pressure between the top part of the wing and the bottom part of the wing. And that difference in pressure generates a net pressure force pointing upward, which we call the lift force. So the lift, right. So this is primarily how a wing works. It works because it has this shape, which is the airfoil shape. And each one of those, now if you take this knife and try and cut this wing from the leading edge to the trailing edge, you're going to see the same, that same cross section, the airfoil. You cut this guy over here, you're going to get the same airfoil section. You get this guy, you're going to get the same airfoil section, and same thing with this guy. But you see, the lift generated on the main wing is pointing upwards. The lift generated on the horizontal, on the yawing wing is actually perpendicular to the surface area. So that makes you move left and right. And these aren't supposed to, they're not designed to generate lift, but they're designed to
maneuverability.
They're designed to save fuel by reducing the tip vortex. So we will have one of those tokes on these tip winglets. We call them tip. Right.
Is it actually used to prevent having vortices over the wings?
To reduce them, yes.
Okay.
To reduce, we call this the root of the wing, and this is the tip of the wing. And at the tip, there is a vortex, which you actually often see over campus when airplanes come to land, and especially on humid days, you have those long lines behind the airplane. And what they are is the condensation from the engine, the CO2, when you burn hydrocarbon fuel, you get CO2 and H2O. The H2O comes and gets trapped into these tip vortices, and they condense, and you see them as little long lines of cloudy vapor. And just because they're air that's rotating at high speed, it means that they have energy. And where do they take their energy? They take their energy from the airplane. And if you try to break them somehow by putting a winglet, you will actually reduce how much they spin, the amount of energy that they have in spinning. So you get less energy lost from the body of the airplane by doing this into the air. Okay, now let's look at, again, we're talking about nomenclature, what we said, leading edge, trailing edge. This is the root of the wing where it's attached to the fuselage or the body of the airplane. And that's the tip of the wing and the distance between the two tips of the wing, tip 1 and tip 2, is called the span of the airplane. So this is your span. Now, if I look at a top view of an airplane, the span is the distance from the two tips, and then the top view shape of the wing is called the planform. So here you have a trapezoidal type of planform for this airplane, and here you sort of have a rectangular planform. And you will see different types of planforms for the wing. So you can have rectangular ones. These are the old, the historic ones. High-speed aircraft, like supersonic aircraft, have a triangular planform, or compound type of planform, such as the space shuttle. It has a triangular and a trapezoid. I don't know how you want to look at it, but it's a compound type of system. And a Boeing 747 has a swept back, so you'll see you have this angulated backwards type of a swept back trapezoid. So that is the Planform, and in fact the French would have. So now we have talked about two things that describe the wing: its cross section, and two, its Planform. And this is what designers spend their time doing is to perfect the combination of the Planform with the best cross section to give you the performance for that particular application. So if you want the least amount of drag, maybe you want to sweep the least amount of drag with the most stability, maybe you want to sweep them back. You want to sweep your wing backwards, put more of the load in the area concentrated closer to the body of the airplane. Also for structural reasons, you would like to concentrate most of the lifting load closer to the body of the aircraft. So it's got application. Is your application speed? Is it maneuverability? Is it energy consumption? You want it just like with cars. Do you want to go fast? Do you want to pay less fuel? And now all these aircraft have different personalities, just like the different cars that you are familiar with. So you buy a Toyota for reliability and fuel efficiency. You buy a Ferrari if you want to go fast and you have a lot of money. Again, now you have all these considerations, and it turns out that different schools of thought. So the French would have a certain way of thinking about things, different than the Saab in Sweden, different than the Airbus in Toulouse, different than Boeing in Seattle. So they have their type of thinking, and the Chinese are now thinking in a different way too. So they're coming up with their own applications. So it's all based on what is your objective final outcome? What do you want it to do? Right. This typically would require. Let's see. This typically would require my airplane model, but since I can't get to my office, I can't get it. But I think we will stop here, and next time we'll start talking. I think I would like to record this and annotate it in a much better, clearer fashion, so that you can all follow along in a very easy way. But the things we will talk about next time is the wind speed, which we have covered in fluid mechanics. We talked about wind speed, ground speed, why, when. In fact, we can open it to discussion here. If you, just for maybe 5 minutes, if you take a helicopter, climb up to 1 kilometer above the surface of the Earth, and you know that the surface of the Earth, or the Earth actually rotates around its axis. If you climb up in a helicopter and wait for an hour, are you going to land in the same place, or are you going to land in a different place? Any inputs on that?
I think we would land in the same place because they rotate together.
So here, let's see. I think there was something here called. Just wait here. I can do polling actually. In fact, I would like to try this since we're on options. Okay, so Your question, same place, land in same place, or move with the rotation, or at different place due to rotation. Let's just try this polling mechanism, see if I can. Just bear with me, guys, here. Add an answer. Same. Add an answer. Different. Open poll. Okay, so okay, guys, can you see this? Users of video conference.
Yes.
Okay. In progress.
Sir, is it related to viscosity, the air?
Is it related to viscosity? Definitely it is related to viscosity in the general scheme of things, yes.
Professor, we're assuming that there's no wind, right?
Yeah, we're assuming it's a calm day.
Okay.
I can't see the whole question.
You cannot see the question? You need to, where are you seeing the poll? Where are you seeing the questions?
There's a poll and I agreed to do it.
In the chat.
In the chart?
No, in the chat. You can see it in the chat.
Oh, in the chat. Oh, you can see it in the chat.
Yeah, can you type it in the chat?
You can press more options, and there's the polling option. Just press on it and it will appear. If you're using your phone.
Yeah, but the question isn't coming. Like, I can't see the full question. I can only see the first sentence.
Oh, same here. Yeah, I can see also on my terminal. I can't see the full question. Oh, actually, just put your. Oh, you can't put your mouse on it. But if I put my mouse on it, it'll give you a little pop-up that says gives you right. So it's truncated because of the tabulated WebEx issue. Okay. So, anyways, let's close poll and move on. And we've got. So 50% say it's the same, 10% say it's different, and there's 25% who don't. It's close. Waiting to submit responses. Anyways, so I would like to show you a picture here that I had. I deleted it just yesterday. I didn't feel it was important, but I'll get it now. So the answer is it's going to land in if there's no wind, it's going to land in the same place. And why is that? Any idea why it would land in the same place?
Not leave the Earth's orbit, so they rotate together.
The
aircraft did not leave the Earth's orbit, so they are still orbiting together, so they will move together.
I think
similarly,
okay.
Doesn't this have anything to do with the rotational momentum?
No. Who said the atmosphere?
Even it's 1 kilometer above, due to the rotation.
Someone said about the atmosphere is rotating at the same with the Earth.
with the Earth's surface.
With the Earth.
So because the plane is located within the atmosphere, within the Earth rotation, so it wouldn't be affected.
Exactly. I'm trying, as you're speaking, I'm trying to find this picture that I'm probably gonna find it here, just to show you the relative. Okay, so if you look while I try to find it, if you look at the diameter of the Earth, what is the diameter of the Earth? Any idea? In terms of kilometers, it's around 12,000 kilometers, right? And what is the thickness of the atmosphere? Thickness of the atmosphere? It's so.
About 700 kilometers.
So really, the
I think around 400 something kilometers.
right. That's where the International Space Station flies at 400 kilometer altitude, and that is considered outer space. So 99% of the mass of the atmosphere actually exists within 100 kilometers from the surface of the Earth. So if you look at 100 kilometer in thickness compared to a radius of 6,000 kilometer, you're looking, it's like you're playing basketball in the winter and there is some a droplet of water sticking on your basketball. That's why the droplet of the water, which you can think of as the atmosphere, just sticks to the surface and moves at the same rotation as the atmosphere. And now, because in aerodynamics, now this takes us to our. This takes us to our question back as to wind speed and ground speed and all these things. Since on the ground, the helicopter is sitting on the ground, but once it is lifted up, it is sitting on the air. And since the air is the atmospheric air, and since the atmosphere is attached to the surface of the Earth, from thousands and millions of years, then the airplane is moving at the same speed as, or is in the atmosphere, which is tucked to the surface of the Earth. I don't know if that makes sense.
I have two questions about this.
Mm-hmm.
Yeah. So the first one, basically, when the helicopter lifts up, the higher part of the atmosphere is actually rotating at a faster velocity than the lower part of the atmosphere, basically because it still occupies the same place, because they have the same angular velocity, so it has a higher linear velocity, the upper part of the atmosphere. So when the helicopter lifts up, wouldn't it gain some kind of other velocity when it's at 1 kilometer away from the surface of the Earth?
So that was the question. Is there wind, or is it a quiet? And we said it is a quiet, a quiescent, non-windy day. So yes, you can have even wind at the surface of the atmosphere. And if you have wind blowing in a certain direction, and you're able to stabilize your helicopter, it will drift. Of course, it will drift just because it's attached to the atmosphere.
Okay. Something else, I'm not sure if it's related to our topic, but they usually say that traveling from Seattle to Paris takes less time than from Paris to Seattle.
That's absolutely right. That's exactly the point.
Okay, so I don't really get it. So how this is actually correlated with the rotation of the Earth, right? And so how
not in a direct way, not in a direct way, in an indirect way. The rotation of the Earth creates what's called jet streams, and these jet streams are just winds. I don't know if you've seen the cartoon movie Finding Nemo, the fish.
Yeah.
Yeah, so I know you can get on one of those highways.
Same thing in the sea, right?
Exactly, there are currents in the sea and there are currents in the air, and you can just ride into that highway and it'll take you where you want without. It's just a stream of water or stream of air. So there is a jet stream at a latitude, I think, of 30 degrees and also 60 degrees. There are two of them. There's actually one at the equator, and then at 30 degrees, minus 30 and plus 30, I believe. So these will take you from Paris to New York. So let's see, does it take longer from Paris to New York or from New York to Paris? The jet stream, so let me just pull out a picture of the jet stream so that we talk about the same thing. I think that would be easy to do. Jet stream. Well, yes, that's exactly the point. Is the relative speed and ground speed is what allows you to move at a different speed going east or west. So let me just insert this tensor picture. Okay, so probably you can see this, right? Can you guys see this picture?
Yes.
Okay. Yeah. So here, these are the jet streams. You have here's your polar jet stream and then you have subtropical jet stream. But this is the one that actually, and it's not steady in its place. It has some average position, but it deviates left and right around its average position. And it's not steady all the time, but it's some kind of average phenomena that happens, just like saying it's cold in the winter and it's hot in the summer. But it can be, you can have cold days in the summer and you can have warm days in the winter. But on average, there is this type of flow phenomena around the altitude where airplanes fly. At what altitude do they fly? Around maybe 10 kilometers, 20 to 30,000 feet. Typically, that's where commercial jets fly. And if you try to ride in this, you're sitting in that atmosphere as if you put a piece of a paper towel. It's just going to, if you put a paper towel in this jet stream, it will actually travel from point A to point B. And that's why you have, sometimes you can have salt being carried by the atmosphere from point A to point B, salt being carried from being thrown by the sea, ejected by the sea, flying up into the air currents, not necessarily in the jet stream, and being thrown in a different place. You can have, sometimes they say in the news, maybe you've heard that it had rained fish on a certain place, and that's completely possible just because fish can jump in the air and updrafts can take them and land them somewhere else where it would be raining fish on an inland location, and which is perfectly makes sense. And same thing if you try to ride. If you put your airplane in this jet stream, this brings us to the relative velocity, which we want to talk about next time.